All right, good morning. Good morning. So it's May 6th today, and I'm glad you're all here. And we're going to start off with something a little bit different. And I know I told you guys to bring your periodic tables, which you guys will use. But I wanted to show this. Hold on, let me just pause this. Okay. I wanted to try that Jeopardy together because I think it's pretty interesting that it actually popped up on my screen. I'm just going to pop it up right now. And this is actually yesterday's Jeopardy category, and it was on my YouTube, and it's about chemists. I don't know how many of you remember chemists or give it a try. I remember watching this. Yeah, I enjoy watching Jeopardy, as you all know, and yeah, give it a try. I don't know what you guys think, but let's give it a go.
The category is chemist.
Chemist 1200.
Here's our special guest.
And it's Bryan Cranston, so it's Breaking Bad guy, so it's great. This one, I would say, like this one was the tougher question for sure. It's 1200 question.
Folks weren't happy with the Nobel Committee's decision to give the 1918 Chemistry Prize to ammonia synthesizer Fritz Haber, as he had also overseen Germany's production and use of this on World War I's Western Front.
Anybody with this one? This one is a little bit tougher, but like we will talk about Haber's process about making ammonia. There is a big significance to his contribution too, but this one is a little bit challenging because we haven't really talked about what he did. So it's okay if you didn't know about this one.
And
What is mustard gas?
mustard gas or poison gas? Yes.
Chemist 16.
Back to Brian.
Ready for this one?
Russian Academy of Sciences rejected this great man's 1880 nomination for membership, maybe because of his progressive political leanings, and maybe because he proposed to a much younger woman while he was still married to his first wife.
Ken.
Anybody with this one?
Who is Mendeleev?
Yes.
Chemist.
I keep pushing the mute button. The guy who discovered or came up with the periodic table, Mendeleev, probably recognized from him from the picture.
For 2000.
Real-life scientists whose names came up on Breaking Bad included, of course, Heisenberg, and also this Frenchman, guillotined at age 50 after...
Hold on a second. I'm messing up my screen here. Things are not working well right now, as you can see. Hold on a second. Oh, this is what I want. Sorry about that. Move up. There we go. Now my face is up. Okay. This guy, Frenchman, guillotine at age 50.
Chemistry, a modern science.
Brad.
This guy, the guy named as the chemistry of modern science, he's a huge, we're going to talk about him as well, especially some of the stuff that we'll be doing. But he was guillotined, and there was a huge story about him too. With Marie Antoinette as well. He's like super, like this chemist was really wealthy and had all the sort of the resources to do a lot of his experiments, which makes you sort of question like, or all these scientific discoveries made by people who have the resources because they have, resources and people at their disposal. Makes you wonder, right?
It was Lavoisier.
Yes.
Chemistry.
Lavoisier.
Visitors at Paris's Bibliothèque Nationale must wear protective gear and sign a liability waiver to study her notebooks, which are stored in heavily shielded boxes.
Well, this one should be very doable, right? Not many female chemists are out there, or female scientists, I should say, and she won 2 Nobel Prizes.
James.
It was Marie Curie.
Right.
Marie Curie.
Chemist 4.
Auguste Laurent and Jean-Baptiste Dumont hated each other, but they worked together to pioneer this branch of chemistry that focuses on carbon and the carbon compounds found in living things.
This is all about carbon, which we actually have a unit on this, which hopefully I don't know if we'll get into, but it's a pretty significant branch. It's called
James.
What is organic?
organic chemistry.
Brian Cranston for that category.
That's right, organic chemistry. So hopefully y'all have fun with that one. I don't know if you guys are even watching this. Let me fix my screen here because there's so many screens going on here. Boom. There we go. All right. Yeah, so Isla, you got it. Madame Curie, that's great. So what we'll have now, oh, I didn't know that. There's so many screens going on here. So last time we talked about the moles and we talked about conversions, and I think this is a great time for us to go back into that question that I posed before as one of your assignments. Some of you calculated this, some of you didn't try it, but let's give it a go, because now we know moles and we can calculate molecules, and it's pretty interesting because this happened in the springtime, right? So I'm just going to show you this video again and see if you can tell me what you think about the calculations here. I have ice in my backyard. It looks nice in the wintertime because everything's frozen, but in the springtime it actually gets very messy. So you can see I've been trying to speed up the process by breaking it up. One interesting thing is that every time I break like large chunks of ice here, it looks pretty light because it's just ice, but it's actually quite heavy. So if you look at this massive chunk, it's quite heavy. So my question here is that can we calculate how heavy this is, right? I have a measuring tape right here, so let's just calculate this chunk of ice right here. So in order to do that, we would have to, I'm kind of out of breath here after moving on the ice. Let's look at the volume of this, right? So let's just kind of measure, my shadows. This is about 5 inches in depth. And let's just kind of, for simplicity's sake, let's just kind of make this into a square. So if we were to just kind of assume that triangle doesn't exist, and then we'll get some dimensions here. Let's go, this is about 19 inches in height, and then across is about 21 inches across. So if we were to have a cube of 19 by 21 by 5, how heavy would this be? So you would have to assume the density of water is just at 1, so let's just assume that this is pure water, and see if you can calculate the grams of this. If you need to, probably have to convert this to kilograms. And if you want to challenge yourself, how many molecules of water will exist in this cube or ice of water? So if you can do that, give it a try, because this one is not even the big one. You can see that there's a bigger chunk here, and there's like a continent over there sitting over there. So that was so heavy that I can't even lift it up. So this is here's your challenge, so give it a try. So that's the ice chunk. So let's kind of go over how we can do this, right? Like, really, this question is really just based on your conversions, right? And you can see my backyard, like this was a couple months ago, and it was cleaning up after the ice rink is never always fun. But this is somewhat like a math question, and if we wanted to extend into chemistry, we can really look at how do we calculate the molecules, right? So if we were to break it down, this is really what the chunk looks like, right? This is obviously, it's a perfect sort of symmetrical chunk, and we did a lot of assumptions on this. But here's the dimensions. So this is 5 inches, and then this is 21 inches, and this is 19 inches. This is all in that imperial measurement system, in which we don't like. So I have provided you with the conversion factors to convert all this stuff, right? So 1 inch is 2.54 centimeters. So first thing I would do is convert all this stuff before even calculating the volume of this, right? So let's just convert all this. So if I were to convert inches into centimeters, I'm just going to do this, right? I'm going to have my inches here and my centimeters here. My conversion factors is 2.54 over 1 inch, right? Because you know that inches will cancel out. So let's just quickly convert all these. Let me kind of get my calculator here, and then I know some of you have done this already, and which is great, because that was really the challenge. But I think it's nice to now know, like, what's the applications for mole conversions and molecules and all of that, right? That's really why I wanted to show you this, because now instead of just doing like a question on a sheet, you can actually calculate something that's real life, right? So let me just kind of quickly go and convert all these ones. I'm just going to go times this by 2.54. So 19 times 2.54 0.54. This one is 48.26 centimeters, and then the last one is 5 inches. And then again, so this is sort of like the work you want to show. So when I marked some of yours, I was looking for the work and looking at how you guys did it with the work that you have shown. So this is all in now a metric system. Right now we have centimeters, because why we want centimeters is that this is a volume, and we actually have a conversion, like a direct conversion from a volume to like a liquid form, right? A milliliter volume, right? So we wanted to convert this to a metric system first. So the next thing is, well, what's the volume here, right? You know the volume is length times width times height. So I'm going to multiply all this together. So I'm going to have 53.34 times 48.26 times 12.7. Multiply all of that together. This is my volume. 32692.19 centimeters cube. And because this is water, we can make the assumption that one cubic centimeter is 1 milliliter. This is for our water based on our density. And so then this is really just the same as 32692.19 milliliters. So we basically changed that cubic centimeters to milliliters based on that. Okay. And then the next part is that now how do we convert this into grams or pounds, right? That's the tough part. So then one important part here is that you need to know the density. So this is the next step that you have to recognize. Density is going to be your mass over volume. Okay. And we made this assumption here, right? The assumption of density of water is 1 gram over ml. So this is for water. So if you have pure water, the density is just 1 gram of water in 1 ml. So basically the density is 1 is equal to the mass, which we're trying to find, over 32692.19 milliliters, right? So this might be the confusing part, because the density is, well, where do we get this density from? Well, this is really the formula. The density is equal to mass over volume, okay? So the next part here is that I'm going to isolate and solve for the mass. So then I'm going to cross multiply this. I'm just going to multiply this to that side. So really you're multiplying by 1. So you're going to get 32692.19 grams. That's the mass of that ice chunk. Okay, so that's where we have. And then the next step is that, well, how can I convert this to pounds? Because we don't really know how heavy a gram is, right? So let's change this into pounds. So that's the next conversion factor. So we know that 1 kilogram is equal to 2.2 pounds. Okay, so let's change this. First, this is in grams. I need to change this into kilograms. 1 kilogram is, so these are some of the conversion factors you might want to know now, is that 1 kilo means 1,000 grams, right? 1 kilograms is 1,000 grams. So what you're going to do is basically to convert this grams into kilograms, you're just going to divide by 1,000. So you're going to take this and move this 3 times to the left. So once I have done that, then I'm going to have the new unit of kilograms, which is 32.69219 kilograms now. So instead of having grams, I have kilograms, right? So then now with the kilograms, I can convert to pounds. So I'm going to do this times the division bar. I'm going to have kilograms at the bottom and pounds at the top. And 2.2 is up here, so I'm going to put 2.2 over 1. And then multiply all this. And I know some of you have calculated this already, because I have marked some of your answers and you all got it correct. And the answer here is 71.92 pounds. So that chunk of ice weighed like 72 pounds. And even though it didn't look that big, but it's very heavy, right? So I think just like moving some of the stuff, I probably hurt my shoulder doing that, because my shoulder still hurts. That's not even the biggest ice chunk, right? There's a bigger ice chunk that was probably like 4 times as big. So if you imagine, that's massive, right? So the next part here is that, well, how do we calculate the number of molecules out of this? So here's the tricky question, right? The molecules. So in order to calculate the molecules, well, we know the mass here. We have to go back to the mass in grams. So anytime you're using moles and all that, it has to be in that metric system in grams. So let's not use pounds, but go back to grams. I have 32,692.19 grams. And then the first thing I want to do, how can I convert this to moles, right? So if I were to convert this, like set this up as a unit analysis, I need to get rid of this grams unit. So grams has to be at the bottom, and then I want the moles. So that's first thing, right? So then how do we get moles from here? Well, what unit gives us grams and moles together? Well, now this is what we learned on Tuesday or Monday, sorry, is that your molar mass from your periodic table gives you 18 grams per mole, right? That's what we learned. Where do we get this 18 from? Well, if you look at the composition of hydrogen and oxygen, there's 2 hydrogens, and each hydrogen is about 1 grams per mole, and then 1 oxygen is about 16 or 15.99 ish. So that's grams per mole. If you add all this stuff up, you'll get 18 grams per mole. That's where that number is from. So you're going to put that number into here. So are you going to put 18 at the top or at the bottom? Well, remember it says 18 grams for 1 mole, so that 18 is tagged with the grams, so 18 goes with the grams right here. And then the moles is per 1 mole, so I'm going to put 1 here. So you're going to do this, and then you're going to cancel out the grams, and you're going to left with moles. So then you're going to calculate, divide this 32,000, because let me punch this in, 9 divide by 18, and then you're going to get this number of moles, 1816.23 moles of H2O. So then once you have the moles, then you can actually also calculate the molecules. Remember, when we do molar conversions, before we convert to grams, like the mass, or to like anything, you have to have moles first. Moles has to be the central unit. So the next part is that I'm going to take this 1816.23 moles. I'm going to set this up as my unit analysis. I want to get rid of moles, so I'm going to put moles at the bottom. And what I want to find is the number of molecules, right? So I'm going to put molecules at the top. And what number is going to give us the molecules, right? And you remember from last time is your Avogadro's number, so 6.02. We'll put an extra 2 here, times 10 to the 23 over 1. And then cancel the moles, and I'm gonna see if I can punch this in. I got really bad allergies right now. Boop, 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 boop. So finally, you're gonna get 1.094 times 10 to the 27 molecules. So in that chunk of ice, that's the number of molecules of water that you have. Okay. Does that make sense? I know it's a challenging problem. It's a challenging thing because it's like real life application. But sometimes, the things that you see, if you can calculate the grams of it, and if you know what it is, you can probably calculate the molecules or like the atoms from it based on Avogadro's number, right? So that's like a real life application of molar calculations. So just to recap about on Monday is that your molar conversions, this is what we did. We looked at this ultimate conversion triangle. So what it is that this is it's moles is a conversion unit, or I should say like a unit of measurement, like a dozen, and 3 things can come from that mole conversion. So grams, that's your mass, so the unit is in grams. Number 2 is anything like particles, molecules, atoms, anything like that. And in order to do that conversion, you need Avogadro's number. And then the last one we'll talk about is your molar volume. So that's the last conversion that we'll talk about. Okay, so if I were to move into the molar volume here, let's see. We can even calculate zombies. Okay, molar volume. So this is the last conversion, and it's really straightforward. Like I said, I don't want you guys to stress on like memorizing like what numbers I need to use. A couple of numbers you just need to know is that you need to know like molar mass as the units grams per mole, and that's from your periodic table, and it varies from element to element. So that's number one. Number two is your Avogadro's number. Like you can't go, like you have to remember Avogadro's number, and I think after doing like tons of problems on this, it's not that bad. And then the last one that you can convert is molar volume. So you can notice that this is in the volume. So the unit here is liters. So that's your SI unit is in liters. And the tricky part here is that this molar volume is just in gases. So what it is saying here is that 1 mole of any gas at STP, if you remember what STP is, standard temperature and pressure, that's your 0 degrees or like your 1 atmosphere, has a volume of 22.4 liters. So what that means is that if you have 1 mole of, let's say, of O2 gas, if you have 1 mole of that, that means that you have 22.4 liters of volume of gas. If you have 1 mole of CO2, a different kind of gas, you also have 22.4 liters of it. If you have 1 mole of, say, like nitrogen gas, same thing. You have 22.4 liters of it. So that's really what molar volume is, because if you think about the physical structure or properties of gases, they can expand, right? So when you're looking at gases, it doesn't matter how many moles you have, because the gas behavior expands. That they're going to fill 22.4 liters of it in 1 mole. So if you even quickly think about like how many molecules are there, you're going to notice that 1 mole of oxygen is going to be 22.4, and it's going to have this number of molecules, the Avogadro's number, right? Because 1 mole has this number of molecules, right? So this number of molecules is going to be found in oxygen, also going to be found in carbon dioxide, also going to be found in nitrogen. So basically 1 mole of any gas is going to have this number of molecules. It doesn't matter what kind of gas it is. Small little oxygen gas or bigger gases, it doesn't matter. If you have 1 mole of gas, you're going to have 22.4 of it. That's it. Okay, so that's your last conversion. That's what I talked about already. So let's look at this one as an example. A cylinder of O2 gas occupies a volume of this. So at STP, and you're going to be asked how many moles of this are in the cylinder. And even after that, you can basically calculate how many molecules, right? So I don't care about any of that. I don't care about like if I'm dividing or multiplying. Like I really don't want you to do that. I want you to use that unit analysis, because it helps you understand your units so much better than memorizing. I can tell you that when I was in grade 11 chem, I memorized this because my teacher told me that, oh, to go from this, you divide. To go from that backwards, you multiply. So then I memorize and memorize and memorize. And sometimes, you know, when you memorize something and you go on a test and go into a test, and then sometimes you might panic and then you second guess yourself and you might forget, right? So it's better to know like a technique to understand how to do it. It makes it so much better, right? So let's try this out, right? I'm gonna write what I'm given. So 60.50 liters. I'm gonna set this up as my unit analysis. Well, that's a weird line. Let's choose a different color here. I want liters to be at the bottom. That's not much of a different color. That's what I want to get rid of, right? That's why it's in the opposite. Like this is in the numerator, this is in the denominator, right? I want to find moles, so I put moles at the top. Now you know that there is a unit that has moles per liter, right? You know that, so that is okay. So you know that there's a moles per liter. You know that this is gas, so I'm going to use this molar volume, and I'm going to substitute my standard 22.4. So 22.4 is sort of your conversion factors. Conversion factor, I should say. Oh, this should be not liters per mole. Yeah, sorry, it is 22.4 liters per mole here. That's what you want. I'm just going to cross this out. And then this is for every 1 mole. So I'm going to cancel out the liters. And now the math here is that it's 60.50 divided by that. So I'm going to punch this in. So 60.50 divided by 22.4. And you're going to have 2.7 moles of O2 gas. That's what you calculate. Can you convert how heavy this is, the mass? Can you convert the number of molecules? Yes, you can, right? Because now once you have the moles, you can basically convert to whatever you want. I can say that 2.7 moles times division bar, put moles at the bottom. And if I wanted to say, well, how heavy is, what's the grams of this volume in 62.5 of oxygen? I can do that. I can put grams at the top. And then now I need to figure out what my molar mass is for oxygen, right? So remember, for oxygen is O2. I'm going to be 2 times 16, 15.99. I'm just going to round it to 16, and it's going to be about 32 grams per mole. And I'm going to put 32 up here and per 1 mole and multiply this. I know this is not part of the question, but I want you to start thinking about, like, hey, what can I do with moles? Instead of just focusing on the question, you can actually do a lot with moles here. So I'm going to multiply by 32. So in this, my moles are going to cancel out, and my final answer is 86.43 grams. So in this volume of 60.50 liters, I actually contains 86.43 grams of oxygen. So that's from the mole calculation. Okay. For the next one, let's see. For this one, a tank is filled with neon gas at STP. The tank has a capacity of 18.0 liters. How many moles are in the tank? So this seems like a very basic question now because you're just converting this to moles. How about we'll change this to find the moles and then find the molecules that are found inside. So this is like a part 2 question. So the first thing you want to do is, what should we do, right? I'm going to write 18.0 liters. Make sure you have your units. I'm going to set this up in times division bar. So liters is going to be at the bottom because I want to get rid of it. And let's solve for moles because that's what I want. So I'm going to put 22.4 at the bottom for every 1 mole. So notice that my units and how they're oriented. And I'm going to cancel out the liters. Liters will get canceled. And what I'm going to do here is that it's going to be 18 divided by 22.4. And I'm going to get 0.80 moles of neon. And then after that, that's really the first part of the question. Super easy, right? Like, I mean, you just solve for the moles. So I'm going to take this, and if I wanted to calculate the second part of this, I'm going to take the moles, and then I'm going to do another division bar. So moles is going to be at the bottom, and now I want molecules. So what number do I use for molecules here is that I want to use the Avogadro's number. So 6.02 times 10 to the 23 over 1. And then please stop me if you have any questions. Just type it in the text here. 6.022 times 23 times 0.8. So I calculate this to have 4.82 times 10 to the 23 molecules. So moles cancel. Now I have molecules of this nitrogen gas. Okay, so you can now figure out how heavy something is or how many molecules you have based on moles or the molar volume of this, right? So that's really it about molar conversions. And we'll talk more about, we don't even have to go over this one. This is just more molar conversions. I'll just delete this because we talked about that already. And after today, we're going to move into stoichiometry, which still sort of uses your unit analysis. But if you want to go ahead, you can watch the video on stoichiometry. But make sure you guys know how to do the molar conversions for sure, because it is very crucial for you to know how to do this. Make sure you finish pages 83. 84, because after that we're going to go into stoichiometry. If you want or need more practice questions, let me know, because there's tons, it's all about the practice for setting up your unit analysis. But really, that's it for molar conversions. Yeah, so let me know if you have any questions. I'll pause here. I'll just wait for you guys to get caught up, and if you have any questions or any comments, just let me know, and I'll just kind of pause here, and I'll let you fill that in. Okay. Yes, thanks, Annie. Man, I talked for like so long without realizing. Yes, Isla. Use scientific notations for sure, because I think as now you progress into higher level sciences, no one really uses the super small numbers. No one really uses to write out all the big numbers. Get a habit of using scientific notation. I would also recommend you guys to make sure you know how to use your calculator. So what that means is that if you're typing it in your calculator, don't type in like times 10. You should have a function that says exp or ee on your calculator. Use that. So to give you an example of this, if I'm typing Avogadro's number, I'm not going to do this 6.022 times 10 and then do that little hat. Don't do that. Okay, if I'm typing it in, I'm going to put 6.022. Oh, I didn't put the 6 here. 6.022 like this. And then I'm going to put exp for my calculator. Exp. That already gives you that times 10. That gives you that exponent. And I'm going to put 23 at the top like that. That's what you want. Okay. So you don't want to put that times 10 for sure. And then with the little hat, because the syntax of the order of things might screw up your calculations. Answers for 83, I would have to take a picture and upload it to your workbooklet key, and 84 as well. Yeah, I have it. It's all here. I just have to put it up. Maybe I'll do that after this stream. But that's, yeah. Let me know if you have any other questions. I think yeah, give those 2 pages a try, because on Monday we're gonna go into stoichiometry and all that, and I think probably like by the end of next week we'll wrap up this unit. Unfortunately, there are not any labs that we can do right now. Maybe we'll think of something for you guys to do at home about like stoichiometry, but yeah. I have released this quiz on, I think, average atomic mass, naming, and types of reaction. So on your OneNote, or not OneNote, on your Teams, there's this quiz that I just released at 11. It's going to be open for like next 2 days. Make sure you guys try that. It's, again, multiple choice question. And yeah, so once you finish it and then hit submit, I think you'll get your feedback right away. Make sure you try that in the next couple of days. I think it is a really good idea for you to keep up. Oh, it says biology. Yeah, yeah, I'll change that too. Because I do biology streams too, right? So sometimes like all the settings for my live streams are just reuse. So I go from like here, and then I have my bio tomorrow, and then yeah. So that's why. So no questions. But if you do have any questions, let me know. Allergies are really getting to me because like my nose is all stuffed up right now because of allergies. It's not COVID-19, but yeah. So take care, everybody. Okay, I'll see you on Monday. Okay, all right. Take care. Bye.